Okay, let's get started. Last time we derived the grand canonical distribution, sometimes known as the Gibbs distribution, and the big reveal in the lecture was this picture here on the lower left, where finally I explained to you what it is that we're actually doing in statistical mechanics when we talk about these reservoirs and ensembles and different distributions and things like this. Actually, it's very simple. We've got an isolated system. It's very big. And in the middle of it is some subsection that we draw a blue box around in the air and say, that's the thing that we're calculating, not everything else. And then particles are going into and out of that section. And since they're going into and out of it, they're carrying energy. So the energy is fluctuating in that region. The number of particles is fluctuating in that region. And so it's very reasonable to then remove the restrictions on constant energy and constant particle number. And as we'll see, that makes it easier to calculate. And the reservoir is just the rest of the box. That's not the thing inside the blue region. And the system of interest is the thing that's inside the blue region. And both of those things are macroscopically big so that we can look at the large systems limit, at least for most of what we're doing in this particular course. We defined the Gibbs free energy, and then we derived the Boltzmann distribution, the Gibbs distribution in the now familiar way. I'm not going to go through that again. And I asked you to check some of the very simple identities that come from computing expectation values, thermal expectation values in the grand canonical distribution by differentiation of the grand partition function chi. So what we're going to do today is we're going to finish up that by I'm going to introduce you to a new variable called the fugacity, which is just so the exponential of the chemical potential. We'll talk about the grand canonical entropy and the grand potential. Remember, for the Boltzmann distribution, what we did was once we knew the Boltzmann distribution, pi is e to the minus ei over kt. Once we knew that, we then plugged in that into the definition of the free energy, and then we ended up deriving how the Helmholtz free energy is related to the partition function, and we saw that e to the minus the free energy over kt is just equal to the partition function. Now we're going to do the same thing with the grand canonical distribution, and it's going to be a slightly different formula, but basically in the same spirit. And we're going to need these formulae because when we start to do many body systems, these formulae actually are very helpful to us in developing a systematic formalism for dealing with many-body interacting systems, which is what we really care about. So we're going to talk about that, and then we will discuss the truly classical statistical mechanics, and we're going to see now why it is that I pretended that we were doing quantum statistical mechanics all this course up to now, which we have been doing formally, but in some mostly classical limit way. So why didn't we just start off with classical statistical mechanics and then go to quantum statistical mechanics? Because usually you think that classical is easier than quantum, but in fact it's not true. Actually, quantum is easier, and so I will explain that, and then we'll end today's lecture most likely by summarizing what are the different formulae for the different distributions in the classical limit. All right, so let's do it. So I want to start off by reminding you what the grand canonical distribution is. So it's over here on the top right, and the I here, of course, doesn't mean energy level, it means quantum state. And that quantum state, that I, is now visible on not just the energy, but also n. And so you can see that it really is not an energy level, but a state. And when we talk about it, we mean a quantum state, including how many particles are present. So first of all, tell me how many particles in the state, then I construct a Hilbert space for that, and then I make a tensor product of all of those things. And for those of you who know a little bit more stat mech than we're going to be quantum mechanics and stat mech than we're doing here, that defines a thing called a Fock space, and that's a simple way, a mathematical way to handle conveniently these types of things when you have processes that annihilate and create particles. So what I want to do next then is introduce for you the fugacity. So I've done that over here. Whoops, something happened. There we are, fugacity. So let's get started with that. So the fugacity, we're just defining it like this. This defines the fugacity. It's a useful variable to define, as you'll see later on. So that's just a name for now, just some weird name that hasn't, with a, which no idea what it actually means. And then in terms of the fugacity, the grand partition function is written in the way that I've shown you. Okay, so that's the fugacity. Now I want to talk about the grand canonical entropy. So the grand canonical entropy, we're going to define that in just the same way that we did for the Boltzmann distribution. So we're going to define it as minus KB, the sum over states I of PI log PI. And by the way, whenever I write down log, just somebody asked me about this, I always mean log to base E. And if I've got lots of space, I write down log. If I don't have much space, I write down ln, which is natural logarithm, but it's always log to base E. Okay, and so that's the definition for the same reasons that we did for the canonical distribution. And now if I substitute in the formula up here for what the PIs look like, and then take the logarithm, then what I get is that this is equal to minus KB, the sum over I, PI times minus EI minus mu NI, let's see, over KT minus the log of chi, like so. And so what that means is then since the PI times E is just the expectation value of the energy, i.e. U, and the same thing with N, so I can write this then as T times the Gibbs entropy is equal to U minus mu times the expectation value of N plus KBT log chi. And actually I can see lots of misprints in my printed notes. So I'm going to switch to the other, to my handwritten notes, just to follow those. So I have that. And remember, I had defined the Gibbs free, we had defined the Gibbs free energy as G is equal to U plus PV minus TS, where now S is going to be the grand distribution entropy, grand canonical entropy like that. And if you remember what I showed you last time, is that G actually is the chemical potential of the pressure and temperature times N, and N is like this, or I'll write it perhaps more accurately as expectation value of N, like so. And so now if I plug this definition into the line above, then what you will find is that minus KBT times the log of chi is equal to U minus T SG minus mu N, and then that is equal to minus PV. So now we have the interesting result that if I define the grand potential, everything is very grand in this. I don't, why, I don't know. So we call it the grand potential capital phi, and that is defined to be minus KBT times the logarithm of chi, just by analogy with the Helmholtz free energy, which is minus KT log Z, the partition function for the Boltzmann distribution. And then just putting those two things together, you can see that that is equal to minus PV. And so please check this algebra as well to make sure that you understand it. And I'm going to just, I'm not going to spend a lot of time on this, but as before, the grand partition function, etc., gives the same results in the thermodynamic limit as the microcanonical and canonical distributions. And the reason, again, is that if I look at the probability distribution, say for the energy as a function of energy, that's going to be sharply peaked around the expectation value of the energy with some width delta E, which is much less than the expectation value of E. And similarly, if I look at the distribution function for the particle number, that is the same story. And so that's the reason. Okay, so now we've introduced all the different distributions. Now I want to talk about classical statistical mechanics. And I want to really ask the question, why did I start off using quantum statistical mechanics? Why didn't I just start off using classical statistical mechanics? So the question is, why didn't we start off with the classical case? Why use quantum mechanics? And in fact, you may be saying, well, when was classical statistical mechanics invented? Well, Boltzmann really was the person. Maxwell and Boltzmann were the people who really first started doing the first what we now would call classical statistical mechanics. But they ran into problems, and we already answered one of those problems. So one answer was the Gibbs paradox. And if you remember, the Gibbs paradox was, where does this 1 over n factorial factor come in to give the entropy being proportional to n? So back at the turn of the century, Gibbs already realized that this didn't really work out. He really came across the problem when he was thinking about two gases mixing together. So this is sometimes called the Gibbs paradox for entropy of mixing, but it's even there just with a pure system. So we saw that there was a 1 over n factorial that we had to put into our formulae. That 1 over n factorial we learned, and I also posted, by the way, this in the channel about the discussion sessions that we have on Monday afternoons. That really comes from the fact that in the classical limit, it's very unlikely to have more than one particle per state. If you have very high energy states populated at high temperatures, then the number of permutations of how many particles, how you can redistribute the particles amongst the states is n factorial, and that's the origin of that n factorial. But it's only an approximate formula. It's only true in the classical limit, where the number of states occupied is is much less than the total number of states of the system. So at high temperatures, you have many states that could be potentially occupied, and then some particles are occupying those states, and most of the states are unoccupied, and virtually no states are occupied with more than one particle, and that's where the 1/n factorial factor came from. So we understood that, but in order to understand that, that explanation required us knowing what is a state. And so that is not the case. There are no discrete states in classical mechanics. So in classical mechanics, there's no real notion so that's part of the reason. So it's impossible to understand the cyclotetrode formula and the entropy being extensive and so on without understanding without using statistical mechanics. So without using quantum statistical mechanics. So that's the first thing. So we are going to discuss that. So then you might say, well, what goes wrong if we start with statistical mechanics, with classical mechanics? And so we're going to take a look at that. So we're going to ask, how would you formulate this classically? And we're going to see that this problem of not knowing what a state is means that you can't really define what the entropy even is absolutely. So the answer is there is no proper understanding of absolute entropy. So in quantum mechanics, we could say entropy is a number of quantum states. In classical mechanics, all we can say is entropy differences. We don't know how to define the entropy up to some arbitrary constant. So classical, entropy differences can be calculated. But not absolute values, but not actual entropy. And so where did this come in to be a huge problem? It came in to be a huge problem when you started to look at the low temperature behavior of physical systems. The entropy as a function of t seems to go to zero. I'm going to put that in quotes because I'm going to say a little bit more about how that works exactly. And so this became known as the third law of thermodynamics. So it was a postulate. People said, well, something's fishy here. What happens at low temperatures? So Nernst and other people said, well, it has to be something like this, but why it should go to zero, there's no reason in classical mechanics. There is a reason in quantum mechanics. And so we're going to see that. So this was a huge rabbit hole that everybody went down at the beginning of the 20th century, trying to understand the third law of thermodynamics, and so we will talk about that. So that's another thing that goes wrong when you don't really understand quantum statistical mechanics. So let's get started then, and we're going to start off with phase space. We're going to talk about phase space, and what we're going to talk about is Hamilton's equations. From classical mechanics. So in classical mechanics, we specify a system of particles by Qi, which are defined as generalized coordinates. And Pi, which are generalized momenta. And the I here goes from 1 to 2 all the way up to 3n. So in other words, in 3 dimensions, you have for each particle labeled by I, you have Qi would be the x position of particle I, and then there'd be yi, and then there'd be zi. So this would be Qi plus 1, Qi plus 2, something like that. So I'm going to let you figure out the notation, but in general we would say you choose your particles, and then each particle has got 3 coordinates, x, y, and z, and so and that's how you define the Qs, and then we make a phase space is a 6n dimensional space whose axes are the Qi and the Pi. So I've got a space that looks something like that. And then what you're supposed to do is you say, well, let's take my system and let's put it represent it at time t as a point in this space. So at time t, this point represents all 6n coordinates at that time. And then now I run the time evolution of the system. So now it's obeying Newton's equations of motions or Hamilton's equations. And so this point then moves to a new point in that phase space, say over to here. And then in general, what happens is it makes some big trajectory like so. And that picture is all of classical mechanics. Okay. And so you might ask, well, what generates the trajectory? And that trajectory is generated by Hamilton's equations. Hamilton's equations say the following: Qi dot is equal to plus dH by dPi, and Pi dot is equal to minus dH by dQi, and I goes from 1 all the way up to 3. And so those are Hamilton's equations, which are equivalent to the Lagrangian classical mechanics and to Newtonian classical mechanics. Everybody here has seen these equations before, right? Right. Okay. How many people here have seen them and forgotten them? Okay. All right. This is the only thing that's useful about having classical mechanics as a prerequisite for this class. This is the only bit of classical mechanics that we will ever use. All right. Now remember that there are conservation laws. So generally, so for most systems, if the energy is conserved, then the energy itself is the conserved quantity, which is the Hamiltonian as a function of all its coordinates, so qi and pi. And so what that means is that this trajectory is not a trajectory in the whole 6n-dimensional space. It is actually on a manifold of that space, a manifold of one dimension less, because every point on that trajectory has to conserve energy, and so it's exploring a manifold with dimension 6n minus 1. And then if I have conserved momentum and conserved angular momentum, then it's 6n minus 7 is the dimension of the manifold in which the thing is going. Okay, so that's your quick review of classical mechanics. Now let's talk about what we mean by an ensemble average. So the notion of what we're doing in statistical mechanics is we're saying, well, okay, we're looking at a system, but we're looking at it in, let's say, a long time limit, or we're looking at it when it is in equilibrium. And so the question that we really want to ask is what is the distribution of these trajectories on this phase space? The distribution of trajectories on this phase space. So that's the question. So let me just make that question a bit more precise. So let's go back to our picture at the top here, and let's suppose that we started over here and we made that trajectory that I've shown you in green. Now let's suppose that I start my system over here, and now I make the trajectory, and it does something like this, right? Okay, so now I started with that, and then you say, okay, fine. Now let's suppose I'd started at a different place, let's say over here, and then what trajectory will I get? So then I go and run the system and I get something like this. And so you get the idea then that if I'm doing statistical mechanics and looking in equilibrium, I'm looking at long times where I've forgotten the initial conditions. And then what I'm trying to do is work out what is the value of any average quantity that I would want to look at. So the question that we want to know the answer to it's a big mess. So that's that. But why do we care about it? And the answer is that if we're in equilibrium, what we want to know is we want to take some observable, say as a function of time, and what we want to know when we talk about the average value of that, what we mean is the limit as let's say call it T1 goes to infinity of the average value of up to T1 of this quantity f of t dt divided by 1 over T1. So that's the average. So I measure some quantity, could be energy, could be angular momentum, whatever you want, and I'm measuring that as the system evolves in time, and I take that quantity, integrate it over long times, divide by the time, and that gives me the average value. Okay, so that's the thing that we would like to know in equilibrium. And what our hypothesis is, which is called the ergodic hypothesis, is that this time average is actually equal to an average over the phase space. And I'm going to write it down. So what that means is that what I do is I take an integral, I write f as a function of the coordinates q's and p's. I'm going to write them as a vector for now because I don't want to keep writing the particular coordinates. So when I write down q, think of this as being a 3n dimensional vector. Similarly, p, 3n dimensional vector. And then I take the quantity that I want. Then I have a density on this space, q of p and t. Then I'm going to integrate this over the phase space, so it's d3nq, d3np, and then I need to normalize it. So that has to be normalized by the integral of rho of q and p and t over the phase space. So this average is called an ensemble average. And the reason it's called an ensemble average is because you can imagine, just as in the picture on the left-hand side, what I did was I took a whole bunch of copies of the system with different initial conditions, and then I evolved them and drew the scribble on the left-hand side and made those trajectories. So it's an ensemble average, meaning it's the sum over initial conditions of the density of trajectories. Okay, now what do I mean by the density of trajectories? So the density of trajectories is a variable that is that we've called here rho of q, p, and t. So that's this thing up here. And so what you can think of is the way I got that was I took I took a little segment of this phase space, and then I just looked in that segment of phase space, what is the density of trajectories? So I look at all the lines going through it and I count up the density. I'm going to do it in some coarse-grained way, just like we've talked about with density before. So all of that goes through. So what we do is we look at the density of trajectories at or near that point in phase space at some time t. And that is the quantity that I'm going to call rho. That's the density of points in phase space. Okay, so this thing is equal to the expectation value with respect to rho, and this is the expectation value with respect to t. So the fact that those two things are true, they're not obviously the same thing, so that is called the ergodic hypothesis. And ergodic means wandering around. And so that's what's happening in the picture on the left-hand side. Okay, so that's the idea that this thing is true, and how to prove it, it literally is quite hard to prove. And I'm not stating it with mathematical precision, but what I've told you is enough for what we need to know. I'm going to define what rho is, and then I'm going to take Jake's question. So the next thing is, how do we calculate rho? And our answer is, well, what we want is what we're counting is the density of trajectories at a given point in space. So go back to first week of class. First thing I told you was how we count in statistical mechanics. We use delta functions, right? So what we're going to do, so the answer to this question, this is what the strategy is we are going to count the trajectories using delta functions. So that's the first step. And then the second step we're going to do is we're going to use Hamilton's equations to derive a differential equation for rho. And then we are going to look at the long time behavior of that equation. So that's what's coming next. Jake, you had a quick question?
Yeah, okay. So are you saying for like every possible initial condition, we look at all of those trajectories?
Yep. Or you can just take one initial condition and just let the system run forever, and hopefully it should cover the space as well.
Okay, so then we're claiming that it will just like sample the entire phase space.
Yep. 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 That's exactly right. That's the ergodic hypothesis, and you can prove it in the mathematical sense, to the sense in which it does sample it. It doesn't go to every point in the phase space because that's an uncountable infinity. So it goes arbitrarily close to every point in phase space.
And then when you're counting how many trajectories are in some small block, is it like if a trajectory goes in and then out and back through, that's twice? That counts as 2 years, counting how many lines?
Yeah. But you'll see, I'm going to just write it down by delta functions and calculate it. Okay, so now let's and let me just say something. In most cases that you'll encounter, you will not have to worry about summing over initial conditions. You take the particles in this room, you start off with the initial condition, let the system evolve, and it will go through every point in space if you wait, a million times the lifetime of the universe or whatever. Okay, so you don't really have to worry about that. But in some systems, ergodicity gets broken. And ergodicity breaking actually happens at phase transitions. So it's actually super important. And so the whole topic of dynamical systems and ergodicity, how you make the connections between statistical mechanics and deterministic dynamics, chaos theory, and so on, that's a whole course I'm not going to go into. We're going to just skip over all of that. Okay, so let's write down a rho. So here is the way that we write down rho. So I'll write it down, and then you're going to say, oh, that was obvious. Why didn't I think of that? Okay, so what I'm going to do is say it's like this. Well, what I want to do is I want to make sure that in the axes QI, if you tell me what QI is, the trajectory is going to follow a path, which I'll call QI bar of T. And then the same thing for the momenta. So that's a delta function in Q and in P. And then, of course, I have to multiply it from I equals 1 to 3n to make it a 6n dimensional delta function. And then if I'm adding over initial conditions, then I will put in here and adding over the initial conditions, but I'm not too fussed about that. And this this function here is a solution of Hamilton's equations. And the same thing for this function here. So those are the solutions. So let's just remember what this thing is. It tells me a density. So basically you say, okay, tell me what is the density of trajectories near the point Q and P, where you tell me what that is. And I say, okay, you tell me what the Q and P are. So those things are what you give me. I put those into here. I then write down the equations of motion, solve the equations of motion, and work out what is the density of trajectories near that point in phase space. So that's what you do. And now let's work out what is the equation of motion. So what we're going to do is the following. We're going to let's just look at so the thing we want to calculate is d by dt of rho, qi, pi, and t. So that's the thing that we want. So let's have a look at one of the components of that. So suppose I were to give you this, I want to know the d by dt of a delta function of q minus q bar of t. So what is that equal to? So q bar of t is a known function. So I can write this as d by dq bar delta of q minus q bar of t. And then I have the Jacobian of that, which is dq bar of t by dt. And then that I can write as minus dq bar by dt times d by dq of delta of q minus q bar of t. So that's what it would be if it was just a one-dimensional delta function. And then this thing here, this thing here, this is the solution of Hamilton's equations. So now let's do this plugging in now my 6n dimensional delta functions. So I'm going to let you check this. So let me write down the answer. So what I get is that d rho by dt is equal to the sum over I, and then minus d by dqi times qi bar dot minus d by dpi pi bar dot and then this thing acting on rho itself. So it's a first order equation. And then I can plug in, so these terms here, these terms are just given by Hamilton's equations. These are just functions of t. So they are given by these two terms over here. So then what I end up with on the right-hand panel is that this is equal to d by dt of rho is equal to minus, I'm going to write it like this, rho h, like so. And when I write down rho h, that is defined to be the sum over I of d rho by dqi dh by dpi minus d rho by dpi times dh by dqi. So that's what it is, just plugging in the equations on the left-hand side into the equation I get from using the chain rule. And this thing here has a name. This thing is called the Poisson bracket. And so I can, so in summary, my equation is that d rho by dt plus the Poisson bracket is equal to 0, and that is the equation of motion, and this result is known as Liouville's theorem. Okay, and this actually has a nice interpretation. I'll mention it briefly. It's not super important, but I'll mention it because you may run across it and get confused. So this has a nice interpretation. So you can think of the points in phase space as they make this flow. So you can think of this as being the flow of a fluid in 6n-dimensional space. And then the trajectory as it moves is like a velocity field. So what you can do is say the following. So the nice interpretation, nice for those of you who think it's nice, is let's define the position in phase space so that's just the vector q and p. Okay, it's a 6n-dimensional vector. So then the velocity, I can make a velocity field in the 6n-dimensional space, which is x dot. And so that is the vector q dot and p dot. So that is a velocity field. And then I can write down the equation of continuity. For a fluid. That equation of continuity would be d rho by dt plus the divergence of a current is equal to 0. That's like the equation of continuity that you know for charge conservation in electricity and magnetism. And here the current in this space is the density times the velocity. So this is a current in the 6n-dimensional phase space. This is just saying that matter is just flowing and is continuous. So this is what the equation of continuity says. But now, if the fluid is incompressible, then that means that what goes in to a little segment of 6n-dimensional space comes out. So that means that div v is equal to 0. So that means it's incompressible. And so now when I do this derivative, so I have d rho by dt plus I have div of rho times v is equal to 0. That means that d rho by dt plus rho div v plus v dot grad rho is equal to 0. And just expanding the derivative. And if it is incompressible, then this term is equal to 0. Because of this. And this equation, the one I have left, if you look at this term plus this term, this is nothing more than Liouville's equation. Okay, so that's Liouville's equation. You can think of it as the flow of a fluid, an incompressible fluid, meaning I've got all these points, which are the positions of the particles. They're all conserved, nothing vanishes or decays. So therefore, it's an incompressible fluid. The points move around in space in a way that's given by this equation of continuity. And if we want to look now, what is the equilibrium solution? So in equilibrium, what we expect then is rho of Q and P and T. If I take its time derivative, then that should be equal to 0. And when that's true, then rho of Q and P as t goes to infinity, that is going to tend towards an equilibrium distribution, q as a row of q and a function of p, so an equilibrium density of trajectories on that phase space. And we can ask, what are the possible solutions of this equation? So let's do that. So if I want the stationarity, then I want d rho by dt is equal to 0, and then that just means that the Poisson bracket is equal to 0. And so now you can look at what are the solutions of the Poisson bracket being equal to 0. So let's have a look at the Poisson bracket. Here it is. And we can immediately spot two solutions. So take a look at that and look at the structure of this Poisson bracket. So here it is. We're setting this equal to 0. Let's ask ourselves, what are solutions of this? The solutions for rho, for Q and P, what are the solutions of that equation? So there's many solutions of this. It's a differential equation, but you can immediately spot two, and those two are ones that you will know and love. So one of them is very obvious. Okay, the other one, you'll have to do a little bit of calculation and to check that it's true. Gosh.
One solution is just the thing in the parentheses is 0.
Yes, we want this thing to be equal to 0. Yes, so tell me a solution for rho.
0.
Rho is no. Rho can't be 0. Something, yes, those things. Constant, yes. Rho is a constant. Rho is a constant. These two derivatives are equal to 0. Okay. So that's one solution. You can see that rho is equal to a constant. Here's one solution. And you've seen that solution before, right? What is that solution called? Not you, someone else. What's that solution called? It's true. Yes, we've set t equals infinity and we're setting the Poisson bracket to 0. Okay. What is the name of this solution, this distribution of rho? It has a name. Find a name that we invented in the first or second lecture. Andrew, right?
Yeah. I guess it's like the classical version of principle of equal.
Yes, exactly. Right. This is just the principle of equal a priori probabilities. Okay. There's another solution. Okay. I doubt that you'll be able to see this one. You might be able to. Anyone? I will let you check it. If you write down rho is proportional to e to the minus the Hamiltonian Q and P times anything. Let's call it beta, anything. Rho is proportional to that. That will also satisfy it just because of Hamilton's equations, just by plugging it in. Okay, so just so you can check that. So this one is a thing for you to check. That's a good thing to do in next week's discussion session. Okay, so now we're starting to see that this way of thinking about classical mechanics is giving us results that are very similar to things that we've seen before in quantum statistical mechanics. So now let's say, okay, fine. Look, okay, it's obvious that this phase space thing is kind of like a quantum state. So can we make this more precise? So let's embark on that little adventure. So the next thing we're going to ask is, this suggests is phase space something like quantum states? And that's the question. And so what we're going to ask now is yes, in some sense. So what we're going to calculate now is the classical limit of a quantum state. So now we're going to need to use a little bit of quantum mechanics. So how many people here know what the WKB approximation is? Okay, some of you. How many of you know what Bohr-Sommerfeld quantization is? Okay, none of you do. Okay, I'm going to show it to you. Well, did you say yes?
Is that just the path integral is like, you do the path or the integral around the.
Yeah. So I'm going to very quickly skate through this, just to show you. It's quite possible that you won't understand all the nuances of this, and that's fine. You can, if you want to, we can discuss it more discussion session. But let me now explain this to you. So we're going to what we're going to be talking about is semi-classical quantum systems. So I'm going to, as an example, I'm first going to do this with a system with 1 degree of freedom. And its conjugate momentum. So that's what we're going to talk about. This is going to be a quantum system. And what we're going to do is we're going to look at it in the semi-classical regime. So what does semi-classical regime mean? Let's suppose I've got a hydrogen atom. Okay, I know what the spectrum is of the hydrogen atom. The ground state, n equals 0, n equals 1, first excited states, and so on and so forth. The classical regime is when n goes to infinity, when you take it's at high temperatures, so the system is no longer in the ground state, but is highly excited. So the semi-classical regime is where the principal quantum number, n, goes to infinity. So n is much larger than 1, and this is the regime that Niels Bohr used when he came up with the Bohr theory of the atom in 1912 or something like that, and was able to do calculations that explain some aspects of the spectra of the hydrogen atom in quantum mechanics. So that's what we mean by that, and what was discovered in what is called semi-classical quantization. Sometimes known as Bohr-Sommerfeld quantization, was the idea that if I take the momentum and I integrate it, dq, around a trajectory, I'm going to explain what that is, then that actually is equal to an integer times Planck's constant. And actually, to be precise, there's also a h/4 that goes in there, but n is much larger than 1, so it's basically the integral of p dq is equal to nh. And so the idea was that the allowed orbits of, say, an electron and a hydrogen atom were orbits where the momenta and coordinates satisfied this condition. So this is like saying you can only go in an orbit like this, and then an orbit a little bit away from that doesn't satisfy that, and then you have to go a bit further up, and then it will satisfy this condition. And so the point here is that n is an integer. And because n is an integer, that's what we mean by quantum mechanics. So this was the earlier idea of quantum mechanics. So then those integers are the quantum numbers, and that's where the term comes from. So this is Bohr-Sommerfeld quantization, and it was an intermediate form of quantum mechanics before you got to the 1920s, and people then were able to write down the Schrödinger wave equation and matrix mechanics and things like this. So this is what was done, and so n labels the energy eigenvalue. And the energy, as we know, is just for this particle p squared over 2m plus the potential energy as a function of the coordinate like that. And what we mean when we talk about the semi-classical limit what we have is that if I write down the thermal de Broglie wavelength, or write down the de Broglie wavelength, lambda is h/p. That's the de Broglie wavelength. Then what we expect is that Vq varies slowly with respect to the de Broglie wavelength lambda. So if I were to sort of draw kind of a sketch of this, yeah, I may have a better sketch in my notes here. Give me 1 second here. Well, I don't. Haha. Sorry about this, and I just lost my page. Okay. Got it. Okay, so I want you to think about it like this. So if I have my potential like so, so here's my potential, and I've got my particle sort of meant to be sitting over here like this. This particle is meant to be in a high n state. So think about what you know about, say, a particle in a potential well, a square well, for example. So the higher is the quantum state, the more nodes there are, the more oscillations of the wave function there are. So if I were to draw the wave function for this particle, the wave function would look something like this. You know n is much greater than 1, because n counts the number of nodes. And you can see here in my picture that there's many, many nodes. If it was a low energy quantum state, then it wouldn't look like that at all. A low energy state would sort of look like something like that. And that's not what we want. And so what I'm drawing here in this picture is wave functions. So that's the limit in which we are in. And when n is much larger than 1, then we think of the particle as having very high energy, but being much more localized. So the low energy state is poorly localized, and the high energy state is well localized. Okay, so that's our picture. So now let's look at phase space. So I'm going to draw my phase space as looking like this. Like so. And then the picture that that we have is that there's an orbit like this, which has, say, the quantum number n2. Then there's another orbit like this, which has a quantum number n1, and what we're going to compute is the integral of p dq. So let's suppose that I were to draw a little element of volume in this space. So this would be dq. This would be dp. So if I want to integrate dp dq, then that gives me area in this space. And so now what I'm going to do is I'm going to do this integral in the space between the trajectories. And so what is that going to give me? Well, if I know that I have this Bohr quantization condition, then if I go on the blue curve, then the integral of p dq in the blue curve is the area in blue. If I go on the yellow curve, then the integral p dq is this area. But it's also that area also includes the area inside the blue curve. But when I subtract them, so we know that the area in blue, this is equal to this area is equal to n2. This one is equal to n1, and so therefore n2 or n1 minus n2 then is equal to the area which is in between the two curves. So let me just draw it like this. So here are my two curves, and then the area between them is this one. So that's what that is equal to. So I can say then that the integral of n1, the integral of the phase space trajectories. Let's try again. The integral of the phase space trajectories then is equal to, so there's an h that goes in here, and there's an h that goes in here. So this is then 1 over h, like so. And so n1 minus n2 is 1 over h times the area of the donut, as it were. Okay, so what does that mean? Let me write that down in words. So it means that if I have a volume of phase space which I'm going to call omega, then the number of quantum states represented by it is a pure number, and it's just omega over Planck's constant. So I take that integral over phase space. That gives me an integer, and so I take that volume of phase space, divided by Planck's constant, and that gives me an integer, the number of quantum states between those two things. So now, if I had n particles, so that's in one particle. So if I have n particles in d dimensions, then what I'm going to have is this: the integrate over some volume in phase space. Now this is d q1 all the way up to d qn, and then d p1 all the way up to d pn. So that's the volume in phase space or of n particles in d dimensions, and that is going to equal the volume in phase space divided by Planck's constant to the power d and then to the power n. So that means then, so now I know how to relate quantum states to an integral over phase space. So what that means is that if I write down the classical partition function for a gas of n particles in d dimensions, with Hamiltonian h of the p's and the q's, like that. What is that going to be? Well, this is the partition function. It's going to be, in quantum mechanics, it will be the sum over states of e to the minus ei over kBt. And in classical mechanics, well, my partition function is now going to be the integral over d3 q1 up to d3 pn, the same thing I have over there, e to the minus the Hamiltonian over kBt as a function of the q's and p's. And then I have to have in there a factor of 1 over h to the power dn. So that's Planck's constant to the power d, the spatial dimension and number of particles. And then I also have my 1 over n factorial, the Gibbs factor, that comes in like so. And this is the direct formula, the classical limit of the quantum partition function. So this is quantum over here. And this is the classical limit of quantum mechanics. So let's just talk about what are the terms that we have here. So why is this important? The first reason is this. First of all, I've got an exact formula for the partition function. In the classical limit. And that means that I can compute the entropy using the formulae that we had before for the canonical entropy. And this formula includes Planck's constant. So that's the thing that is why we did all this. We figured out how Planck's constant gets in to the classical partition function, so that if I were to take the quantum partition function and take the classical limit of it, I would get a Planck's constant in there because I started off with quantum mechanics, and this factor of h to the dn is the factor that you could have guessed to put in to the partition function in order to make the two things coincide. So without having that factor of h to the dn, my partition function would have just some random number in there. The other thing is that if you look at the integral d3 qn d3n p, this thing has dimensions. So our partition function would have dimensions. So in fact, so even if you didn't know that Planck's constant existed, that would make you think, that's really, really weird. You'd say that's really weird. There must be some fundamental constant of nature to make this dimensionless. So that's what you would think. So just doing classical statistical mechanics, you already realize that there must be some other constant that we don't know about, which is Planck's constant. And then we also have our factor of 1 over n factorial. Now 1 over n factorial came from the counting the states, because in the n much larger than 1 limit, most states have 0 or at most 1 occupancy. And that's where the n factorial comes from. So this classical statistical mechanics derived as a limit of quantum mechanics is very, very subtle. It was one of the so we already knew from statistical mechanics that something like quantum mechanics must exist, and this tells you then how to write down the correct formula. So with this formula on the left-hand side, this formula here, this formula is fantastic because now there's no arbitrariness in the entropy. As there was before we knew about quantum mechanics. So we didn't have to say, well, you can only measure entropy differences and so on. No, that's not true. We can measure the absolute entropy because we're counting quantum states. So So that's where I'm going to stop. So the bottom line of all of this is that there was a smooth continuity between classical and quantum statistical mechanics, and the Planck's constant is the volume of phase space occupied by a single quantum state. Okay, so I think we will leave it there. Next time, we will finish with, I will apply this to the cyclotetroid formula. I will show you how we get the third law of thermodynamics and the sort of third law of thermodynamics paradox. And then I will summarize the laws of statistical mechanics in the classical regime, tell you when classical mechanics can be used and when quantum mechanics can be used. And then we will start to compute. The rest of the class will be, okay, how do we now compute the partition function for any system that we actually care about? Okay, so that's the end of today's lecture, and I'll be happy to take questions in just a second.